So it's been a while since we've done these Velo virtual sessions. So I'd say hello and welcome to Velo Virtual. Our plan is to continue these into 2024. Velo Virtual is Velo3D's webinar platform where we deep dive into technical solutions and explore live what makes those innovations so powerful. My name is Mike Rogerson, and I'll be your host today. So I am really excited to just talk about our session today. We're going to talk about and show you an absolutely amazing part. When I saw this part for the first time, it blew my mind. When I saw it in real life, it was even more. So this part, in my opinion, represents the state of the art for metal additive manufacturing in a number of ways. The size, the geometry of the part, the material, all of it. It is next generation. But you might be asking yourself, what started this journey to make this impeller? And for really quickly, let's talk about the energy market. We, at least in the United States, expect persistent energy. When we click a light switch, the power comes on and stays on. And that's just what we expect, whether we're at home, we're at work, or we're in a government facility. And that's not always easy. For infrastructure designed to last dozens of years, the way the industry's infrastructure is designed to last, parts don't always last forever, and suppliers don't always stay forever either. So if you can't get supply and you can't get replacement, how do you keep the lights on? One solution that we're finding out a lot of companies will do is to stock large inventory. A large inventory does reduce the risk of a supplier exiting the market, but obviously it's expensive and can trap large amounts of working capital that could be invested in other areas of the business. And eventually inventories do run out, leading to a possibility that you have a multi-million-dollar asset out of commission, waiting for a $10,000 to $15,000 part, something like that. This is why a lot of leaders in the energy industry are turning to metal additive manufacturing. The ability to print parts quickly and then have them machined in a matter of weeks changes the dynamics of supply and demand. By reducing the risk of part shortage, inventories don't need to be as large. Operators can now access a digital inventory. They can source parts in weeks, and they can get original part specifications. So that's one solution, or maybe in some cases move to a new alloy, optimize the design. These are all possible with metal additive manufacturing. So to help us learn a little bit more about what makes this possible, I'd like to introduce our speakers for today. Dan Lavertu is our Technical Business Development Manager at Velo3D, where he works with customers to help them fully leverage additive manufacturing technology. Prior to joining Velo3D, he worked in various mechanical engineering roles at Lockheed Martin, Ehrlichen AM, and Kozlowski Additive Manufacturing. Dan has a Bachelor of Science in Mechanical Engineering degree from Rowan University. Also joining us, our VIP guest is Ben Wagner. He's engineering manager at Rotating Machinery Services. Ben offers a wealth of experience as an aerodynamics engineer with a focus on developing and testing military helicopters. Ben contributes over 15 years of performance analysis, wind tunnel and flight testing, airfoil analysis, rotor design, aerodynamics, and conceptual design. Ben has also led the design of several centrifugal compressor re-rates. So, Dan, I will turn it over to you.
Thanks, Mike. Hey, everyone. So before I get into everything, I just want to, I know some of you might not be aware of, who we are at Velo3D. So Velo3D was founded in 2014, and we're actually the only major metal AM manufacturer who designs and produces our systems in the US. We became a public company in 2021, and what we offer is a fully integrated metal AM solution. It enables the production of complex and high-value parts. Along with that, we also provide service and support across the globe. So what do we mean when we say we have a fully integrated solution? Our main offering is our family of Sapphire machines, but Velo has developed and integrated its own preprint or print preparation software, Flow, and its quality validation software, Assure, into our machines. So together, it's really how we are able to help our customers with expanding their design freedom, the repeatability across our machines, and really just controlling our process a lot better. It is important to note that there are individual solutions for some of these softwares, but it's really how Flow and Assure are integrated into our family of machines that really gives you that overall control of the process. So here are some typical parts that you would see from our technology. What you'll notice through all of these is that they're all very complex with internal features, and that's typically where we excel with our technology. So space was a great application to kick us off as a company. So you'll see, like in the middle there, we have a copper nozzle, and we've also have a lot of experience with like thrust chambers and other high temp alloys. But we've also been doing a lot in the energy industry as well, which, like we're talking about today with the impeller that we did with RMS. We do a lot of volutes, a lot of flow parts, and so it's not we started with space, but we really do see a future in the energy industry. So here are some of our customers across the industries. You can see we're not just working with space or industry. We're actually working across multiple industries. And along with our customers, we also have our network of contract manufacturing partners, and we work closely with them and helping them, supporting them with working with all of our end customers and really supporting them. So if we just take a step back and just looking at the AM industry as a whole, so our technology is really laser powder bed fusion. And right now, that's the largest market in the metal AM industry. This is mainly because the process yields high quality material and feature resolution in a variety of alloys. And as the technology has been advancing, build sizes have been increasing, and the metallurgy has been getting a lot better. So in some materials, you can even find that the material properties in AM are actually rivaling forged materials. So you can see even in this graph here, you can see that as we're going along in time, that demand is starting to increase for this technology. So how does laser powder bed fusion work? For those of you who don't know, it's a pretty simple process, and in its most simplistic form is you have a piston or a build environment, a build volume that is on top of a piston, and that piston steps itself down depending on a layer thickness of that process. They're on the range of microns. So that piston is stepping down layer by layer, and every time that piston steps down, there's a recoater arm that is distributing the powder over that platform, and then a laser is coming in and melting that two-dimensional cross-section of the part. And then it's repeated over and over again until you have a full part. So naturally through this process, there's a lot of stresses induced. And so if you're familiar with 3D printing with polymers, there's a lot of supports that are needed. It's a little bit different than what you see in polymers. In polymers, you're using supports to hold the part up. But in metal additive, you're actually anchoring the part to your build plate. Like I mentioned, there's a lot of stresses being induced through this process, through the welding process. And so your parts want to peel up like you're seeing here. And so what's typically happening is that's peeling up out of the powder bed and crashing into that recoater arm that's distributing the powder. And obviously that is not going to yield a good result. So what Velo 3D is working towards is not needing any supports and really eliminating that need for design for additive. And why is this important? This is a really good case study here to show the importance of supports or the lack of supports. So for an impeller, conventionally, you're going to have some angles in that part that are going to require supports, especially internally, like you can see here. And so the solution to that is typically tilt the part, and that will eliminate a lot of those low, shallow angles, and it will eliminate the need for any supports internal to the part. But now this part's being built at an angle. So now, since this is a layer process, your part's no longer symmetric along the axis. So being able to print that part flat without any supports internally is really ideal. So now your part is symmetric. So when it comes to balancing and spin test and spinning the part, you're in a much better place there. And then also with finishing the part, trying to get supports out of the internals of a part is sometimes extremely difficult or impossible. So like I said, the ideal state is being able to do this process without any supports. So where does this come into play? With our Flow preprint software, this is where really all the magic happens. It's where we're importing the CAD files. It's where we're applying our supports. It's where we're applying our processes, our laser processes, and we're even slicing the build file within Flow to create a print file for the machine. So something different that with our preprint software is actually that we take native CAD files instead of an STL file. Conventionally and typically throughout the industry, you will need to use STL files, which requires you to export that CAD, your native CAD, into an STL, and a lot of times there's a loss of data or there's a lot of inconsistencies when you start doing that translation. So being able to just import your native CAD file has a lot of benefits for that. And not only with the inconsistencies, but Flow can then read those features and identify those features for strategically placing or applying our processes to the build. So what's unique about Flow is that instead of typically you have your preprint software will go and slice your build file to whatever layer thickness that build is at, and it's applying that process to that two-dimensional slice only. So what's unique about Velo is that it's actually taking account, because it can see those features, it's actually taking into account the geometry above and below that current slice that it's applying the parameters to. And then what's really good about Flow is that all of this is feeding into a print file, right? So there's no longer importing your CAD into your preprint software, applying your supports, and then exporting that build file and pairing it with a laser parameter file to create a print file in a separate software. This is all happening within Flow. And that print file can then be used on any machine around the globe with that has that material in it without any manipulation to that print file. So once your print file is coming out of Flow, it's all locked down after that, and changes really can't be made to it, which is really, again, trying to control that process. And then with our Sapphire printer family, so we actually have several different machine sizes. Like I mentioned, it is laser powder bed fusion. And so we have 4 main sizes. It's our Sapphire. Our Sapphire is our smaller frame machine, which is only about 315 millimeters in diameter. And it goes up to 400 millimeters in Z height. And then we also have our Sapphire 1MZ, which is the same diameter, but goes up to 1 meter in height. And then that same thing copies over to our Sapphire XC. The main difference there is the diameter increases to 600 millimeters. And for the smaller XC, it goes up to 550 millimeters in Z height. But then we have the XC 1MZ, which also goes up to the 1 meter in Z height. Some things to note about our machines is that on the Sapphire machines, they all are equipped with 2 1-kilowatt lasers. And then on the XC, they have 8 kilowatt lasers, 8 1-kilowatt lasers. So you can imagine that with our Sapphire XC, we have a significant increase in throughput with the 8 lasers. On all of our machines, those lasers are going through an in-situ laser alignment as the build's going along, which I'll touch on some more in a little bit. And depending on our materials, we can build in different layer thicknesses as well. So our standard has typically been the 50 micron layer thickness, but we can go all the way up to 150 micron in some of our materials. So talking about some of the unique features of our system is our recoding technology. So what I mentioned earlier about how things are typically recoated. It's just a single blade. And what we actually have is a multi-step process. We lay down a very thick layer of powder to begin with, and then we use that hard blade to smooth out that layer. And then we come behind that blade with a very fine-tuned vacuum to then bring it down to the resulting build layer, or that, let's just call that 50 micron build height or build layer. And so what that's doing is actually allowing the part to protrude a bit outside of the powder bed and allowing a little bit of flexibility with, like I mentioned earlier, when you're inducing that stress, it's allowing that flexibility of the part to somewhat flex out of the powder bed and start to be able to build lower angles without it crashing into your recoater blade. Another feature is our multi-laser alignment, like I mentioned earlier. So our laser alignment is actually critical to both the material and your geometric quality of the parts. So before we start any build, we're actually taking about 500 measurements and 500 different locations around the build plate to align all the different lasers within the machine. So this is actually automated. This is an automated calibration within the tool or within the machine. So there's no need for any additional equipment to come in, put into the machine to take your measurements. It's all happening just with the click of a button on the machine. And then as your build is running, there's actually checks going on before and after each layer. That is, again, realigning the lasers and making sure that everything is still within spec. So again, like I mentioned, this really helps with your surface finish, your geometric accuracy, and your material properties. And since we are using multiple layers, it's really important to make sure that the 2 or 8 lasers that we're using are all aligned with not just where they're supposed to be, but aligned with each other. And this is a really good example of why this is important. This picture on the right. So as you're building your part and you're getting taller and taller within the build, that build environment is obviously going to be heating up and things could be shifting. And so you really want to align that laser throughout the build so that nothing is shifting from that where that laser is actually supposed to be hitting because of the environment. So I've gone over how our solution can get you a printed part, but Assure is really what is key in validating and monitoring the process. So there's a couple different aspects to Flow that we're using to do this validation. So first, we can actually monitor the entire fleet in real time, all within a dashboard. So like for us, for example, we have several machines at our headquarters, and we can see at a glance all of our different machines and what they're building, if they're having any issues, or the status of the build. So it's all live build progress monitoring. Then we have Assure also helps with our tool health. So I mentioned on the last slide about our calibrations, or our automated calibrations for laser alignment. But that's just one of several calibrations that we're doing before a build. So you can actually see in this little tile here that there's a bunch of green check marks there, and that's for all the different calibrations that we're doing before a build. And the cadence of these can really be determined based on really what that machine is building and what that customer's cadence really needs to be. And then during the build, we're actually doing in-process monitoring as well. And I don't want you guys to get confused with in situ monitoring or closed loop control or anything like that. We are monitoring the system, and we have enough sensors to do a closed loop control, but we're just using that to validate the process and control it. And so you can see, like, we have sensors here for different things in the environment, right? So I mentioned we allow the parts to flex a little bit out of the powder bed. So because of that, we need to monitor how much that part is flexing or deforming out of the powder bed so that we don't have a critical error. So we have sensors that are measuring that peak height, what we're calling peak height, but we're also taking images and topographical scans of the powder bed to show and see where things are moving. And so when we're getting to a limit, you can see this dotted line on this graph. We can set a spec limit. So if that build is getting near a limit, let's say the oxygen is getting too high in the environment and that sensor is reaching the spec limit, it'll send out a warning to the team. And then if it gets close enough to that spec limit, it'll even pause the build to not go above that threshold. So it's, again, Assure is really just trying to make sure that your build is staying within the process that we developed, and it's not giving you results that you shouldn't expect. And then at the end of all of this, as you can imagine, there's a ton of data that is being dumped into all of this. But Assure can give you a nice build report or build information summary that brings all of this data together. It goes over what was in the build, what processes were used, and it really helps you try to document that build so that moving forward, you can repeat that process and have that repeatability from build to build or machine to machine. Here are the different materials that we offer. So one thing I do like to note on this slide is that we have a lot of customers that are looking to use stainless steel because of their legacy designs. And you can see we do have some stainless options, but we also have a lot of nickel alloys. And what's actually really nice about additive is that since there's a lot less wasted material in our process, we can start using these higher performing alloys over some of the legacy alloys. So many of our customers who are using a stainless steel, they end up switching or upgrading, I'll say, to our Inconels or some of our nickel alloys, which traditionally that would be a significant cost increase because of the wasted material. But since you're really only using the material for the part itself, there's really no significant impact to the cost of a part, and you're getting a higher performing alloy. I also mentioned that we have a contract manufacturing network that we partner with. So here are all the locations that we have globally. And like I said, we work really closely with this team, and what our technology is really supporting is being able to allow our end customer to really leverage this network to be able to take a single print file and send it to multiple suppliers and work with all of them and expect the same results. So going into a little bit of designing for our technology, and these next couple slides are really focused on some of the things that we look at when we're working on impellers. So like for RMS that we're talking about today. So one of the biggest things we like to communicate is how you're really orienting the part or designing the part. So when we're growing cones, or in reality, it's an inward growing angle versus an outward growing angle. There's a couple things to take into account with this. So when you are growing a cone, you start to get a ring stress, and that ring really wants to pull in and peel that part up again. And so your process starts to break down. But when you are growing a cone inwards, like the one on the right, that hoop stress is pulling in on itself. And so there's really no need for that material to want to flex up. And it's a much more stable process. And so we can even go down to a 0 degree overhang or angle when we're doing those inward growing cones, because it is such a more stable process. And so everybody's always interested in surface finish and what to expect with surface finish. And a lot of times you'll get the response, it depends. And this is why it depends. You can see as you change the angle of a part or the orientation of a part in a build or the design of a part, as you get closer and closer to horizontal with that or parallel with the build plate, your surface finish starts to take a hit. And again, that's because you're starting to see a lot of those stresses. You're starting to see things want to move and flex. And then you're also getting, different instabilities with the process of, when you're trying to make a part like this and you're hitting it with the laser, you're not having a whole lot of material to penetrate. So you start to get a poor surface finish on the other side because you're now overheating the part and causing that extra material on the bottom side. So you'll see as you start to go closer to horizontal, which is up in this area, your surface roughness is taking a big impact there. And then I got one last slide before I hand it over to Ben. And what I'm really trying to communicate here is that, we have a lot of experiences with impellers that have been cast and forged across different applications, both pumps, compressors, different materials, different sizes, across different customers. And so we're really trying to help push this technology forward. So because we have this experience, we're trying to invite customers to leverage it and push it even further, right? So if we just take a look at this real quick, where we started back in 2020, we started with Hanwha, and this was really an R&D effort of trying to understand and validate material properties and asking basic questions like, does AM even work for impellers? And then later on in 2020, we started working on a centrifugal pump, and we started pushing that envelope a little bit more. And we started making the features a little bit more complex with lower angles. And this was a casted impeller. And so we proved that we could achieve a low angle and have a high quality surface finish with this. And so moving forward after that, we're then pushing it even further with Mohawk, being able to show that we can, at certain sizes, we can actually have a cost advantage over existing technologies. And going through the rest of these, we, started advancing that technology more and more and being able to do bigger, lower angles until we get all the way to what we've done with RMS, where we've now gone from, sorry, I forgot to mention that these ones back in 2020, 2021, these are all on our small frame Sapphire machine, right? So we're vetting out and proving a lot of this on our small frame machine. And then with RMS, we're now getting to our XC size machine. So we're doing a 19-inch diameter impeller, printed flat, with a very low overhang. I think it goes down to below 10 degrees. And so we're proving out now, and we're validating what we need to do to be able to print impellers of this size. Because when you go from that small frame Sapphire machine to a big frame 19-inch diameter impeller, your physics starts to change. And so we have to adjust for that difference in physics. And so Ben will be able to go into some more of those details of what were those hurdles that we saw, and how did we overcome them. But really, again, I'm just really looking to show what our experience has been, but also that we're really looking to expand this timeline. So with that, I'll hand it over to Ben.
All right. So as Dan mentioned, we did this development impeller 19 inches on the Sapphire XC. A little bit about RMS, if I can get the slide to change. There it goes. Okay. So RMS, Rotating Machinery Services, we've been around in one form or another since the late 80s. And originally the company was Conmec, and then RMS was formed later. We primarily service and repair and redesign or overhaul rotating equipment. centrifugal compressors, steam turbines, expanders, power turbines, oil-free screws for the oil and gas, energy, and chemical processing industries. And we have grown significantly in the past few years to vertically integrate to incorporate some what are now our sister companies that help us develop and build more of our parts in-house. Like I mentioned, the company's around 335 employees. We've been around for around 25 years. We are now owned by the Cortec Group, and we are ISO 9001 certified. Several locations. Bethlehem, PA is our headquarters. We also have several facilities in the Houston, Texas area, and engineering office in Appleton, Wisconsin to support the AC compressor product line. So the problem on this project was we wanted to manufacture a significantly, bigger than normal for 3D printing 19-inch impeller, centrifugal impeller, closed. So it's got a cover and a disc with blades. When we do this, typically we start with forging. So in this case, the original design was for 17.4 pH stainless steel. We would buy a cover forging and a disc forging, go through several machine operations, and then weld them together, and then do final machining. So during those several manufacturing steps, there's risk in each operation for things like machining errors or welding distortion or variations in performance between different welders because the welding is all done by hand. And then you can have risks of dimensional deviations due to shrinkage in the flow path from heating in the welding process. We also, at every step, have to go through a lot of non-destructive testing, chemical analysis of the original forging material. And we are hoping that with the additive manufacturing process, we can reduce those lead times quite a bit and get the customers replacement parts or newly designed parts on a much shorter timeline for similar or lower cost. One of the other things that's a consideration that AM gets us is the improvement in materials, going from 17.4 pH stainless steel or carbon steels like 4140 or 4340 to Inconel allows us to tailor our designs for higher strength and higher hardness. Some of the applications, this one is one example, the gases that the product is exposed to in service are what are called sour, which is they're vulnerable to stress corrosion cracking due to exposure to some chemicals like hydrogen sulfide. Because of that stress corrosion cracking risk, different materials, depending on how naturally corrosion resistant they are, need to be kept to a strength and hardness limit, so they can't be above a certain level. And for carbon steels, that's 22 Rockwell C, which gets you in the 90 KSI yield strength range. You can get a little bit more with 17.4 pH. Those stainless steels in that family are allowed up to 33 Rockwell C, which can, get you a little bit more yield strength. But Inconel, because it's inherently much more corrosion resistant, can be 40 Rockwell C in hardness, which gets you quite a bit more strength, even for the same gas exposure risks. So before I get into the advantages, to explain a little bit more about the normal process for manufacturing impellers, there are several, but this is a slot welded example. I mentioned we start from forgings. Those get rough machined and go through heat treatment and inspection. They're then machined into what we call semi-machinings, where the flow path side of the impeller, which will be the inside of the final product, gets machined. So the disc will have blades machined into it, and the cover will have slots. Those align, and they have some features to align them. And then they'll be welded into one component, which is what was shown on the previous slide with the photo. The welds are in the slots to bind the cover to the blades through those slots in the disc. And then once this is done, it goes through a stress relief and heat treatment process to make the welds and the base material all the same metallurgical characteristics and same strength, same hardness, uniform properties. After that heat treatment, it goes through a final machining operation to yield the final part, which is shown here in the bottom right. When we get our forgings, we always buy them with sample rings of material, and those rings of material follow the rest of the metal through all the manufacturing and heat treatment steps so that we can do destructive testing on those samples without actually needing to destructively test the part. And that's to verify those properties we care most about: strength, hardness, make sure we have a ductile failure and not a abrupt fracturing of the part. So all of these manufacturing steps and the quality control and the several heat treatment steps lead to quite a bit of lead time. The conventional impellers can take up to a year to manufacture. Part of that is just there's a lot of demand right now in the industry, and so getting the forgings can be a significant part of that, but then there's a lot of manufacturing steps as well. So additive manufacturing allows us to reduce the cycle count and the number of operations required significantly and get parts quite a bit faster. So here's an example of a slot welded impeller with the welds. So you can see all the welds in the slots, and this is before final machining. And once it's final machined, you don't see any of the welds. The process for slot welding is risky, as I mentioned. We have a lot of experience doing it, but getting that experience is a process in itself. You need to have precise control of the welding process, the materials and procedures, and the stress relief and heat treatment processes needed to get consistent quality. This machine was a 5 impeller compressor, but they range from single stage compressors to 9-stage compressors, and you want consistent quality from one to the next so that you don't have to incur replacement parts that would, set you back in time quite a bit to buying new forgings and making the parts from scratch. So I mentioned a little bit about this. Additive manufacturing gets us quite a bit fewer steps and then schedule improvement that goes with that. There's fewer machining operations and no manual welding. And it will also allow us to do more complicated designs to improve performance and aerodynamic efficiency without any additional cost or risk. This impeller has 2-dimensional blades inside of it, which means that they're essentially vertical on their faces, but single stage machines and higher efficiency impellers have 3-dimensional blades where there's a rake or a lean angle in the blades. And that is more expensive and requires 5-axis milling to produce, but there's no cost impact to do those designs with additive manufacturing. And as I mentioned, the advanced materials like Inconel 718 get us significantly higher strength and improved corrosion resistance compared to other materials that we would commonly use. But there's very little cost impact to that the way there would be if we start with forgings because there's so little material waste. We had done a impeller build with Duncan Machine Products earlier on, is shown on Dan's timeline slide, which was a 10.7-inch impeller, I believe. And the new Sapphire XC with its 600-millimeter build plate allows us to get quite a bit more, opens the market for a wider range of larger impellers. This one was 19 inches in final diameter. We went through some development with Velo to optimize the print and to get the best quality finish in the flow path. That flow path, because it's printed in the impeller, is essentially final once it comes off the printer and doesn't get finished machined. And we want to make sure that we have a nice smooth surface in that. And Velo helped us develop removable pin supports to support that low angle overhang within the flow path without getting any melt pool instabilities, which I'll talk about next. So this is the first impeller that we did on the smaller Sapphire machines. And at this point, we did not have any previous experience with AM for impellers, and we printed the flow path without any supports. And the part came out fantastic and was actually extremely strong. But the one drawback was that on the upper surface, which is almost a horizontal overhang in the flow path, because that upper surface is only supported by powder underneath it, and there were no pin supports in the flow path when printed, we had these little melt pool instabilities. And this picture is after extrude hone polishing, which did make the surface a bit smoother, but because Inconel is so hard and strong, it was not able to really remove those MPIs in the flow path. Now, these are mostly cosmetic. I don't think they would have very much impact on the performance, but it doesn't look fantastic for the customers to see those things. So we want to develop a process to avoid those imperfections. So I think we talked about this. The Sapphire XC, the build plate is 600 millimeters, which allows us to go just a little over 23 inches of final impeller diameter. We have to allow for some rim supports around the outside and a place for the powder to drain out of the final part. This one that we did here was a 19-inch impeller with a nearly flat ceiling. I think the angle inside the flow path was 2 degrees from horizontal. We developed those pin supports through Velo 3D, did an internal trade study, and so the pins are automatically added, that we don't need to include that in our design. Velo's pre-print software takes care of that for us. And the pins are shaped in such a way that they provide the necessary support for those overhung surfaces, but they're also easily removable with very little debris left in the flow path afterwards. As far as reduction in engineering and design time, the number of manufacturing drawings that we need for an additive manufacturer impeller is only 2 compared to typically 6 for a slot welded conventional impeller. And we reduce our machining operations from 5 down to 2. There's a little bit less of a savings in the heat treatment operations just because you still have stress relief, and there's an additional HIP process, a hot isostatic press, that's not present in the conventional manufacturing. So we only save 1 going from 4 to 3 with our heat treatment operations. But those are not usually the long lead items in the build, so that's less of a concern. And the other big benefit is that we're using an automated machine to do all of the powder bed fusion. And so we're eliminating manual welding of the machine parts. And therefore, we're not really subject to variations in welder skill, or somebody didn't have enough coffee or too much that morning, anything like that. So in contrast to what I described earlier with the conventional manufacturing process, when we do an AM impeller, we design with Velo's guidance the final impeller and then add features for supporting it during printing. So here you can see that we've taken the final impeller and added rim supports around the OD, and that supports the disc and cover at the outer diameter. There's also a fillet down to the build plate to give that whole structure support to keep it from peeling up or anything like that. And these little triangles that you can see in the image are openings for powder to drain out after the part is printed and removed from the build plate. You also can't really see in this photo, but we have added a little bit of excess on the upper surfaces and in the bore of the impeller. And that's just to give us some margin for any kind of distortion in heat treatment and an opportunity to do a very small amount of finish machining so that the final impeller is nice and shiny. So that's the print. It goes through some dimensional inspection after the print is done, stress relief operation, and then it's EDM cut off the build plate. It goes through a hot isostatic press operation to make all the metallurgical properties nice and uniform throughout the part. And then it goes through a normal heat treatment for the material. So once it's gone through HIP, we treat it like regular Inconel 718. It'll go through the normal heat treatment for our final properties. And during the build, I haven't mentioned this to date, but we will print with each laser test specimens, and that lets us do the same thing we would have done with the forging material, which is take those samples that have gone through the same manufacturing process as the final part and test them for strength, hardness, chemistry, and grain structure. And that's partly required by API standards, the American Petroleum Institute, I believe. But it also gives us that paper trail and documentation so that we can show our customers that they're getting a high quality part in the end that meets the same quality standards that they're used to from our conventional manufactured impellers. After that testing, we'll machine off the outer rim supports. and do the final machining of all of the surfaces and the bore. And then the supports in the flow path, those pin supports that gave us the good surface quality finish, those can be removed by hand. There's an opportunity here for some additional flow path polishing, which we did not do on this project. And then all that's left is the final machine, which I kind of already covered, and then the dimensional inspection. And here is a few photos of this impeller that we did on the Sapphire XC. You can see in the center is an overall view of the top of the impeller with the cover, the very narrow flow path. And then this is the flow path height at the OD is only less than half of an inch because this is a hydrogen machine. And so that's required for the performance. And then you get a very nice surface finish because of that little bit of excess material we added. And so we final machine the outside. But because we're not starting with a very large forging, the machining time is significantly reduced. I mentioned the opportunity for flow path polishing. We don't have any MPIs on this, but you do have the as printed surface, and it is horizontal. So that's on the back left side of the chart Dan showed earlier, where you have a little bit more roughness. We have not really tried yet printing these at an angle to improve that finish, but you have a as printed surface on the lower surface, and then the upper surface, we just had a very small amount of debris from those pin supports. And so we're going to look at ways to further improve that. And we're also assessing whether it actually makes any difference on the performance, which it may not, especially this is about the highest risk design where you have very narrow flow path. As the flow path gets wider, the impact of these surface imperfections goes down quickly because the boundary layer is a less significant portion of the total flow path width. So next steps for us, I mentioned we're going to look into opportunities for that flow path roughness and polishing. And we've already looked at extrude hone, which does polish up that surface a bit, but we're analyzing whether it matters or not. And once we have that information, we'll be able to share that with our customers just to reassure them that the product will perform exactly as we predicted it would. But we're very happy with this product, and we're continuing to push forward with additive manufacturing as an opportunity for these impellers that fit within the Sapphire XC envelope as a way to get our customers impellers that are designed with higher performance and higher quality materials at a much reduced time frame compared to what we can do conventionally. Lessons learned. The larger build volume allows us to do quite a bit more and service quite a bit more customers than we could with the original Sapphire. That's the 600 millimeter build plate size of the XC. Those pin supports were fantastic at getting rid of the MPIs, the melt pool instabilities, and removing the pins was not an arduous process because of the shaping that Velo developed for those supports. And I mentioned the flow path finish is very good, and that's the one thing that customers have noticed when they look in it is it's not the shininess that they see on the outside, but we're going to show that that's a solvable problem. And there's no structural penalties to additive manufactured impellers. The 10.5 inch or 10.7 inch impeller that we did previously on the Sapphire was Inconel 718 as well, and we overspeed tested that to 25,000 RPM with no distortion or yielding of the part. And I'll mention that normally these impellers, as part of their qualification, get overspeed tested to 115% of their maximum continuous speed. But in this case, we took the part to 175%, and it was in fantastic condition, just like it had never gone through it. Any questions?
So we do have a couple questions, and I'll just dive right into that. One of the questions right off the top is, how does the cost of this process compare to prototyping via expandable mold casting? But maybe we broaden this out to maybe other options that you could have available.
I'll mention expandable mold casting. We have made cast impellers in the past. We tend to avoid it in present, mostly because RMS's business model, we're doing a lot of replacement parts and service of existing equipment. So we're not making hundreds of a single design that would justify making a casting mold. The other drawback with a lot of casting processes is that you can get irregularities in the internal properties of the material, which can cause early failure. So we don't usually start with castings.
Mhm.
But compared to conventional, the cost is similar, but that's starting with a forging or multiple forgings rather than a casting.
Okay. And there's a question, maybe Dan, if this is for you. The materials available for the process, are we able to have commercially pure titanium?
Sorry, struggling to get off mute there. Um, so sorry, can you repeat that one more time? I was trying to find the mute button and couldn't get my mouse to work.
The question, so you listed the materials, and one of them is Ti-64, and the question was, can you have commercially pure titanium?
So really the materials that we're using, the alloys that we're using are made for additive, right? So most alloys can be shaped for additive, but I'm not quite sure if we have or have looked at pure titanium like that. So the titanium we use, which you might have seen on that slide, is Ti-6Al4V. But typically we don't use pure titanium for that.
Yep.
I'll mention when we've done this and built these parts, we do get chemical certs for the materials that are used for traceability.
I have two questions. Oh, go ahead.
Sorry, just one last thing that I'll add to that is that a lot of times there's adders put into some of these alloys for the printing process, which is why you typically don't see pure alloys.
Okay. I have two questions that are kind of similar. One asks, do you have any data on pump efficiency improvements or differences between conventional and metal printed? And then the other one, which kind of seems in the same genre here, is how do the printed impellers compare with conventionally manufactured impellers?
I don't have that data handy. There aren't enough of these in service yet to provide a side-by-side comparison of the performance.
Okay. You mentioned a couple other differences, like in terms of the material strength and on the 10.7. You saw some initial guide. I understand we're talking about a data sample of 1 at this point, right?
For that design, yep.
Yeah. So that they're strong.
They are.
So far, so good. This person asks, I'm a liquid rocket engineer. Are there any regions where the printing service is available using Sapphire XC? And maybe, Dan, if you want to handle this one, getting in a little bit about the contract manufacturing network might be helpful for this person as well.
Yeah. So like Mike mentioned, we have our contract manufacturing network that is really across the globe. So we have several just here in the US, and then I think 2 or 3 internationally. And I believe you said that material was 718, right? Is that what you said, Mike?
No, they just said that they make rockets, so I would
Oh,
assume it's
okay.
probably 718
Yeah,
would
yeah,
be a
sorry.
good candidate for that, sure.
But yeah, we have multiple materials across that network.
Yeah,
So yeah.
Yep. If you're interested in making rockets, we have a number of materials that you might also find useful. Haynes 214, Giracop 42 are probably 2 of the ones that are very interesting alloys. Haynes 214 from the oxygen side.
Another good one to mention is Haynes 282.
Yeah, Haynes 282 seems like the new super alloy of super alloys. I'm very interested to see what kind of applications come out from that. Another question here is, what do we think the internal roughness, like what's the end state on that? How much can it be improved with polishing? And how valuable is it to the application? I think you already hit on this a little bit, Ben. And one of the questions here, another question is, how many times did we build the part to get the final one?
So we did one development build, and it was with a portion of the part. So that's a huge benefit to additive, right? That you can basically just take a section of that part that you know is going to be risky and go and do your development with that. So you're not doing a full up build. But so we did, it was a 1 or 2 builds for the support development to try to hone in the most easily removable supports while also being the most sparse. And then for the impeller itself, like I said, we only did a small section build of it to test out that new parameter or support design. And then we went into the full size impeller, which is the one that Ben was showing.
Yeah, this seems to be a pretty common theme, is like de-risking certain geometries or certain sections, not doing the whole part, but just making sure we've got that down. And I've actually seen where that's been broken up on the build plate, where you have certain risky sections, you do a couple different ones, and that's a really nice feature of additive, is you have the flexibility to do that, and then you put it all together, you print the de-risked version of the final product, and you can have something that looks as good as this.
To answer the surface finish question, the surface roughness and the flow path matters more depending on how sensitive your process is to boundary layer turbulence or boundary layer thickness. So a thicker flow path, like a wider flow path, is less vulnerable, and higher flow velocities make you more susceptible. There's options for, you can either treat it with abrasives, which is the extrude hone polishing, where they pump an abrasive slurry through to polish the surface. And there's also chemical etching options. But again, the chemical etching is going to be maybe less of an option for highly corrosion resistant and highly durable materials like Inconel.
Okay. There's a question: what does the porosity look like on the down skin, and does it help when you apply movable pins, as you mentioned?
Yeah, so when I was on that down skin slide that had like the surface finish on there, what we see is, as you get shallower and shallower or closer to horizontal, you can start to see some porosity on the outer contour of that area. But typically what you try to do is mitigate that by making sure that, those types of overhangs that don't have supports are in areas that are non-critical or that are going to be machined, and then you're machining that porous, I'll call it porous area, away. Or like you mentioned in the question, adding supports will help with that. Those supports will help alleviate or transfer a lot of that heat. And so a lot of those MPIs start to get mitigated, and then the quality of your material also becomes a lot more improved.
I don't think it's really porosity either. I think it's really just roughness.
Yeah, was this part, did it go through hip?
It did.
Okay. So I've seen some before and after hip that it seems to address this a little bit too.
Yeah, a lot of the hip heat treatments will take care of a lot of porosity that you'll see in the process, not just with low overhangs.
Okay. Well, that's all the questions that came through, and we are right on time. So I want to say thank you to our audience today. Great questions. Oh, well, somebody's trying to sneak one in right at the last. All right, I'll take this one, and then we'll say our thank yous. What is the delivery time improvement between, this is a great one to close on, actually, between typical manufacturing and additive manufacturing? And this will be our last one.
So typical manufacturing, if an order's placed today, it's pretty close to a year, in the neighborhood of 50 weeks. If with additive manufacturing, when you start from design, printing, heat treatment, and final machining, it's half of that or less. So it's in the order of 20 to 25 weeks.
All right. Well, we are at time, and that's a great question to close on. Thank you, audience, for joining us today. And thank you, speakers. Thank you, Ben and Dan. It was a great job. Do you have any closing thoughts that you'd like to send out before we close?
Nope. Thank you for the opportunity.
Thanks, everyone.